So this is collage of the potentially the most exciting ones. So LSST or Rubin Observatory is the teeny tiny one on the right. And it's also the least inexpensive. It's not the cheapest, it's the least inexpensive. What sets it apart from any other project is the product of the mirror area and field of view called throughput or attendu. That's what controls how fast we can scan the sky. And because this product is huge, we can scan the whole sky in about a couple of nights. But since we take 2 observations per night, every 3 to 4 nights we'll come back to the same spot on the sky. This is visual comparison between Gemini South. I think the same comparison would work with VLT and other 8-meter class, 10-meter class telescopes. So the primary diameters, the primary mirrors have the same outer diameter. Indeed, the area for Gemini South is even larger, the area of the primary mirror, than for Rubin. But the field of view is very, very different. So you could do LSST with Gemini South too, but it would take you 1,000 years. It would be 100 times slower. That's why we wanted to construct the new observatory. The filter complement will be very similar to SDSS, which proved great in practice. The only major difference is that SDSS Z band was split into 2 bands at around water absorption line at 900 something nanometers. And now we have Z, which is narrower than SDSS Z, and we have a new band called Y band, which will improve our sensitivity to very high redshift objects, like, for example, redshift 7 quasars. We already know approximately what will be per band time allocation. It was optimized using photometric redshifts of galaxies, but also it works well with stellar SCDs and with star quasar separation. The observations will be automated, so it won't be an observer who will be deciding, but algorithm. Although we do have one of our observers here, Alicia Shugart is here. If you want to learn about how it feels already to be at the summit and what we can and cannot do at the summit, you can talk to Alicia. So this shows our scanning pattern, which is about 1,000 times faster than in real time. Each jump in reality will take about 40 seconds. And the colors show different bands. And the black circle shows altitude of 30 degrees. So that's the limit of how low we will go. The cross in the middle is zenith. Big black dot is the moon. And so depending on sky brightness, on lunar phase, on how far it is from a field, you optimize where the next field will be. And of course, you don't want to go very far because you spend time on slowing. So most observations go to the neighboring field, but then you also need to keep track of how many fields you already obtained, et cetera, et cetera. So this is all done automatically. For those of you who work with catalogs and don't look at images, here is a quick comparison between SDSS image that goes to 22nd magnitude. So this is 3 arc minutes across, teeny tiny on the sky. And when you go 5 magnitudes deeper, this is what you get. So when we co-add all LSST data, we'll go 5 magnitudes deeper than SDSS. And this is image from Subaru. They can already obtain the same depth, just they can't go as quickly over the sky as Rubin. So whenever I get tired of Zoom calls and other things, I go and I flip between these two until I am happy again. So why are we here? So one of the data products will be automated image differencing. And within 60 seconds, we will issue stream of alerts, little packets with basic information about every source in difference image that we detected. So most of those may be potentially boring for immediate follow-up. They are not boring in general, of course. Variable stars are very interesting, but most of variable stars, like our library, you don't need to follow in 10 minutes. You can collect light curve and analyze them. But for many other objects, as you know better than me, we need to jump on it and follow up immediately. So that's what we will provide as an input to you guys, and then you will take it from there and become rich and famous. So where do we stand with construction? This is a nice slide that Kevin Reel, our integration scientists at the summit produced. So in the top row, you see 3 computer-generated images. That was our design. And the 3 images in the bottom row are the actual photographs of the system. So we do have all the components. We are now in integration phase, and very soon we will enter commissioning phase. The dome is almost done. It looks done, but it's not done. There are a few details to finish. It was a long saga. It's very late. But at this point, we are beginning to decouple it from the rest of the work. There are still few issues we need to attend to, but by and large, dome is operational, and the few things that remain to be done will be decoupled from the rest of the progress. This is one slide I stole from last review. So it says M1, M3 just installed. It's supposed to say M1, M3 cell. So the black part and the blue at the bottom, that's the primary tertiary mirror cell. It was taken out just a week ago, and now we are going to coat the primary tertiary mirror. We expect to be ready to take first images with commissioning camera in July of this year, and I'll get back to schedule later. Here is a tiny little video clip that demonstrates how agile this telescope is. This is not sped up. The other video was sped up. This one is real time. So motion is fully controlled. You could see yellow cross in the back. That's just surrogate mass. It's not the mirror. So we took M1, M3 cell out, which was in for a few months for testing, and this yellow cross will go back in for a few more months of testing while we are taking care of mirror cell and mirror coating and integrating glass with mirror cell. So testing was completed recently, so we believe it's safe for glass to be mated with M1, M3 cell, and I think in April we will coat the mirrors. It will be all silver. And then by July, we should be ready to have commissioning camera take the first on-sky images. We also have auxiliary telescope. Again, Alicia can tell you a lot about it. She's one of the main operators. So we are using it now to test our software frameworks. We did a lot of debugging, a lot of integration using this smaller telescope that eventually will be used for photometric calibration. It will take spectra of stars, and then we will measure atmospheric throughput using those observations, and that atmospheric throughput will be used to calibrate photometric data from the main telescope. Few words about the camera. This is design image. This is Nadine, our former project manager for the camera. She happened to be exactly the same height as the diameter of the camera. So it's already in the Guinness Book of Records as the largest camera ever produced. You may remember from kindergarten that Yerkes refractor was the largest lens in the world. Now it's this one, which is entrance lens for the camera. The camera is fully integrated, but it's still at SLAC laboratory in California. It was supposed to be shipped about a year ago. We hope it will be shipped in a couple of months, maybe 3 months. I'll tell you later why. Here is another beautiful photo of it. It looks just like photo lens, except it's a little bit bigger. And it works. So there are 189 CCDs, each 16 megabytes, 4K by 4K. Each has 16 amps. Each CCD has 16 amps so that we can support 2-second readout using 500 kilohertz readout. So there are 3,024 amplifiers. And if you look carefully, you can find 3 of them that are dead. But the rest of them are all working. And this is pupil image of Vera Rubin scanning here photographs of galaxies. So camera's ready. We did a lot of EO testing. There were some glitches. We had a major problem with the cooling for the electronics. The cryostat cooling is fine, but there were 2 cooling systems. The other one for electronics was unstable. So about 2 years ago, we had to make a decision to completely gut it out, replace it by a different system that has chiller outside of the camera. So that ate about a year out of schedule. And then we had to assure ourselves that it's stable. So we needed at least 3 months of measurements at SLAC. And during those measurements, we discovered a vacuum leak in cryostat. And so that took some time to diagnose, to find a way to fix it and fixing it. So that ate significant amount of time. And just recently, we found another problem I'll tell you about in a few slides. So before that, let me tell you a few words about data products and where do we stand with software. So software is always a problem with big surveys, big projects. But we had COVID to help us. So while the hardware people were slowed down, software people continued. So we are in good shape with software. Indeed, some of our pipelines are already in production with Hyper-ISO Prime Cam surveys on Subaru, ZTF surveys using some of our products. So we feel confident about our software. It will not be, hopefully, major delay when we start commissioning. We have 3 classes of data products. We have regular data releases, yearly data releases for static science. And then, of course, as you all know, we have prompt data products within 60 seconds alert packets. And then there will be a way for you to upload your code to our data center and do data processing, specialized data processing that we are not going to do regularly, but you can then do yourself on our data center, and then you can choose whether you want to share it with other people or not, etc. So at the high level, what we want to do is not just to get the data, but to produce science-ready data products that then you can use to do science and publish papers. So our pipelines are rather involved. They are more complicated than, for example, SDSS or any other major survey. We are approaching about 1 million lines of code developed in-house, plus I forget how many millions, 3 or 4 of libraries, etc. Here is an example of how we are testing our software on extant data. So we used our auxiliary telescope and a little camera that can get small field of view to produce this image, which is about 1 square degree. So this is demonstrating that our co-adding software works. We affectionately call it kilo degree survey. It's just 1 square degree, but it shows that it works. We also had tests with community brokers, as some of you know quite well. And so lots of software is already being tested, used on Oxtel, on other projects, so we feel confident about that part. Some of you may know that originally we were supposed to use data center at NCSA in Illinois, but meanwhile, because of change in the funding profile from the federal agencies, there is new data facility at SLAC. It's already operational, and data is flowing from the observatory in Chile regularly to SLAC for processing, for storing in databases, etc. Here is a short list of some of cutting edge products, algorithms developed by community for other surveys that are now implemented in our pipelines. For example, PIF for PSF, or Gary Bernstein's astrometry, etc. So, schedule. We were supposed to be done, but we are not yet. So first, we had delays due to COVID, and there were some tail effects, nonlinear effects, that caused more delays than just the official end of the COVID era, especially with large vendors. TMA, telescope mount assembly, was constructed in Spain and shipped to Chile. The dome was constructed by an Italian company, so all those components had to be shipped from Europe to Chile. During COVID, people could not enter Chile for a while. Then things started becoming coupled, and so there were lots of complications, and that's why we got this delay. Then we had, I already mentioned, cold refrigeration system issues. We had to completely replace it. Then there was winter storm at the summit. Then a year ago, there was an electrician who was trying to replace some fuses in a 10 kilovolt transformer, made a mistake, got shocked, and then the whole lab was shut down for 3 months. So it didn't have anything to do with us, but according to the procedures, the lab had to be shut down, and then commission had to come from Washington to see how can that happen. You can imagine. So we lost 3 months there. Then last summer, northern summer, we discovered that cryostat leak. We fixed it, plugged it. We thought we would ship in March. We wanted to do 2 more months of electro-optical testing. And then turbo pump for vacuum died just around Christmas. And so we still don't know how hard it will be to replace that pump. It's not designed to be replaceable. We thought it would never die because it was supposed to be on only intermittently. And it was the expectation for lifetime was an order of magnitude longer than what we needed it. But because of these problems with refrigeration system, we went up and down many more times than we anticipated. And in the end, the poor pump died. So we will know a week from now whether the impact will be a month or 2, with 3, we don't know yet. But as you know, there is public webpage that is updated once per month, ls.st/dates, where you can get the latest schedule as we reported to the agencies. So here is an approximately updated list of things that need to be done for us to start LSST. So we hope that in a few months we'll ship the camera to Chile. That is the last major piece of equipment that needs to go there. Dome will be complete, maybe not in June, maybe a few months later formally, but it's decoupled from the rest of the work, so it's as good as completed, more or less. We are now in the process of integrating glass with cells and putting it on telescope mount assembly. Commissioning camera is already sitting on the telescope. So we think in July, plus or minus maybe a month, we will be taking on-sky images with ComCam. If you don't remember, ComCam from the outside looks exactly like the main camera. The main difference is that there are no 189 CCDs in the focal plane, but only 9, one raft, one of those basic units. So we can do LSST, but 20 times slower with commissioning camera. So it could be done in 200 years if you don't get the main camera. It will be all fine. And so then the main camera will come this year to Chile. We think sometime early next year, we will start taking images with the main camera. And then hopefully by northern summer of 25, we will close the project, construction project, and be done with it. And the observatory is then taken over by NOAR Lab, by the National Laboratory in US, National Observatory. And then we'll start LSST, hopefully before the end of calendar year 25. Starting LSST means that we will let telescope be run by that algorithm, by that program that I showed you in one of the early videos. But before that, we will get a lot of commissioning data, and we will practice not only internal processing, but we will also practice sending that alert stream to brokers, and then you can practice all the frameworks that you are developing. So that all excitement will be happening in 2025. If there is any chance to somehow take data from the commissioning camera this year and make something useful to you in the context of alerts, we'll try to do it. In all likelihood, it will not be in real time, but at least we can test all the software frameworks and debug it, so when we get on sky with real data that we can start doing science. So just quickly what's left to be done. This is our diagram for agencies where we explain to them what we do. Red is mirrors and green. ComCam is blue and the big camera is the bottom. Left to right is time going from 3 months ago to beginning of 25. So one big milestone is getting on-sky images with ComCam. That's around July of this year. So we still have glass integration to complete and then test the software systems and then be ready to take data with ComCam. We think we can do it by July of 24 or so. Camera, the main camera, will not be ready at that time. So there are 2 milestones. The first one is shipping the camera to Chile, which was supposed to be in March, but it will be delayed by unknown small number of months. And then even with this original schedule, it would not be ready in July. It would be later that year. So the red rectangle in the middle shows on-sky data with ComCam, originally planned to be 2 months. Now that we have delay with the main camera, maybe it will be 3 months or perhaps even more. And then once we get big camera on TMA, once we start getting full focal plane images, then we'll go through 2 phases. So commissioning and science validation will happen, and we still have few months of schedule reserve, which is really budget reserve. So formally, we should be done by August of 25. We hope we will be done before then. If not, even if there are additional delays, we can still go for another 3 months or so. So we must be done by November of 25. So these are key dates again, and I will summarize here, and I'm open for questions.
Thank you. Okay, before we start the questions, I just want to point out, for the benefit of the people